All right, so cumulative distribution function for continuous random variables. It is the continuous version of what we have learned. Now, if you recall several lectures ago, and also the previous lecture when we talk about the CDF, we say that it is the cumulative sum of the PDF. So you start with a PDF, and then you start to integrate, or you start to sum until the point you want to look at the function, and then that will be the value in the CDF. The CDF, as you can imagine, because you're doing the cumulative sum, it got to be an increasing function. Okay, it will start with 0, it will go all the way to 1. So that's something that we should expect to see. We should also expect to see something like the jump, which is the discrete case where whenever you have a jump, the height of the jump will correspond to the probability, which is your mass. And in the continuous case, what will happen? We need to talk about that. So let me turn on the computer. Okay, so let me start by reviewing what is the definition of the CDF. Here's the definition of the CDF, where you have this notation, big F. Okay, that's a notation of big F. This big F means that it is a CDF with a capital X in the bottom. That means it is a discrete, it means that it is a random variable. It is a random variable. There's a small x. The small x denotes the state that you're looking at. This small x, when you translate to the probability event, it will be x less than or equals to this x. So it could be that you're looking at the probability. Okay, you're looking at the probability that x is less than certain number 1. Okay, and so that one would correspond to the x. So hopefully this computer is recording. Okay, that's my hope. Okay. All right, so maybe we should show people this slide in case they're watching the video, right? Okay, ladies and gentlemen, we're starting this lecture with a little bit of this technical issues. We are here, and then we are now in chapter 4.3. We just start to talk about the definition of the CDF. And this definition is that when you look at this cumulative sum, you're looking at the probability where your x is less than a certain state. So this is the thing that we discussed the last time, where if you have this PDF and you want to calculate the probability under the curve, which is the area under the curve. So you start to integrate the PDF from 0 all the way to a point. Let's say here it will be A. Then when you integrate up to this point A, correspondingly the height here will be fx evaluated at A, where this is a big F, it means it is a CDF. So how much area will translate to how tall is this point in the CDF. The relationship going from the left-hand side to the right-hand side is an integration, and then the relationship going from the right-hand side to the left-hand side is a differentiation. This thing, if you look at the definition here, it is the probability of a random variable up to a state x. So it would be the integration of some f, let me call it t, okay, dt. It would be the integration from -infinity all the way to x. Now, there are two variables in this integration. One is this t. T is just a dummy variable. It is the variable that you use to tell this integral or what kind of, which axis to take the integration with respect to. So that's a t here. There is another variable, this is x. X is actually the state that you are looking at in the CDF. So when we say that, as we can take the derivative is taken with respect to x, not to t. So here when we say, hey, fx equals to this fx of x d dx, right? So here on the left-hand side, you have the PDF. On the right-hand side, you have the CDF. You say that there's a derivative relationship. Then if we write it out, it would be d and dx of something from minus infinity to x, and then there's a ft dt. So you can see that this x dx is taken with respect to x, not the t inside the integral. Just be careful about these two variables. So that's the definition. And let me go through a few examples with you to make sure that we understand the calculation. Now, again, this CDF calculation is more or less just calculus, more or less calculus. However, the tricky thing here is that we want to make sure that the CDF is evaluated properly across the entire real line from minus infinity to infinity, even for cases where you do not have any probability mass, including the zero, the flat area, you want to capture that. So here is the first example. You look at this uniform random variable, which is a straight line, or not even a straight line, it's a flat line, okay, with a height of 1 over b minus a over the range of a to b, including a and b. And it is 0 otherwise. We want to find the CDF, not just calculating the expected value, but now we want to find the CDF of this random variable. So what is the CDF? Well, the CDF has to be calculated through the integration, which is the usual thing that we do every time we look at this problem. But my practice and my advice is that let's look at the diagram first. Get a feeling of how the CDF should look like. So I start by drawing the PDF, which in this case, it would be a boxcar function, right? It will be 0, and then suddenly you have a 1, and then you go to 0, not 1 over b minus a. Okay, so it will be that would be the shape of your PDF. And then how do I get the CDF? Of course, I'm going to integrate, but let's don't talk about integration. Think about cumulative sum. Okay? That's the best way to think about CDF. This cumulative sum, of course, I need to accumulate from minus infinity all the way to the point that I want to see. So let's say I'm looking at the point here, okay, a point just here. I'm accumulating all the mass up to this point. Do I have any accumulation? No. Okay, so it has to be 0. When will I start to have some accumulation? Well, you will start to have some accumulation when you go to this point. Right? So it will, when you see the cutoff, then you will start to see some increase of this area under the curve. So that's why you should expect to see something going up. And then after you have gone through this rectangular function, you should expect it to stay there forever, which is the 1. Right? So you already have this picture of start with 0, go all the way to 1, something going up. Now, how should this look like? Well, this is just a flat line, and so as I move my cursor to the right-hand side a little bit, I should expect the height to go up correspondingly a little bit, and it's going to be a linear relationship. Right? So it should be a straight line going up. It shouldn't be like a sinusoid. It shouldn't be like a quadratic. It should just be a straight line. Right? So without doing an integration, I should have an idea of that shape. Then you do the integration and check whether it is true or not. So now when you have this concept in mind, then you go to this CDF. How many segments do I need to worry about in this CDF? 1, 2, and 3. 3 segments. Not just the stuff in the middle. I actually have 3 segments. The stuff in the middle would just be, of course, integration. The stuff in the left-hand side, stuff on the right-hand side, they should also be calculated. But let's start with the easiest one, the one that we're all familiar with. Let's start with the middle one, the integration one. Okay? So the integration one, which is the integral of this 1 over b minus a d, let's call it t. Okay? Let's call it t. This is the PDF. Taking the integration with respect to t, where should be the starting point? I'm looking at this middle segment. where should be the starting point? A. Okay, A. We should start with A. Where should we stop? Where should we stop? If we stop at B, you'll get 1. We shouldn't stop at B. Okay. So here's a tricky thing, right? We're evaluating the CDF. We're not evaluating the entire. We're not evaluating the entire PDF, right? We want to look at. We want to see. Hey, if this is my X, where is the height in the CDF? So I need to tell you to look at the thing, right? Where it should be the X. Because the left-hand side, it is a CDF evaluated at X, and therefore the integral has to go all the way to X. That's the cumulative sum. Sum all the way to X. You start with A because anything before A, it is 0. That will be the integral. And then we ask, how do we evaluate this integral? Well, of course, you pull out B minus A, and then you just do this dt from A to X. Then, of course, you get X minus A divided by B minus A. So that will give you this equation, which if you look at this thing here, it makes sense. It is a linear function. It's going up. And the slope is B minus 1 over B minus A. Okay, 1 over B minus A. Thank you. So this is a slope. So slope is 1 over B minus A. And it will start at what point? On the x-axis, where will it start? It will start at A. Okay, it will start at A because this is your x. Your x will go from minus infinity all the way until you see the A. Then you will kick off. Now, it makes sense to the equation because if you put an A here, replace the x by A, you get 0. This is the starting point. The end point will be B because you can check if you put x to B, then you get 1, right? So it's going up from 0 to 1. This is the middle segment. Now, I'm not done yet. I also have 2 other segments. What should be the 2 other segments? Now, of course, I tell you that this is 1, this is 0. But we can also write down the definition. This is 1 over B minus A. Sorry, this is not B minus A. That's a dt. That's a dt. The integral has to go from minus infinity all the way to your x. Again, this is x. This is not A. This is still going to be x because you are looking at this CDF evaluated at x. Okay, so you are looking at minus infinity to x. But what should be the stuff inside? 0. Okay, there's a 0 inside because your PDF is 0 for this segment. So it is 0, and therefore you get a 0. This gives you this 0 here. This 0 doesn't come from nowhere. It comes from this integral. How about the last case? The last case, it will be what? It will be the integration from minus infinity, okay, again to x, right? Now, this integration has to go from here minus infinity, including this entire rectangular pulse, okay? So that will be 1 over B minus A. Okay, that will be 1 over B minus A. And then there should be another thing. There should be another thing, which is the 0. Okay. So then in this case, if I want to do this integration, I need to change this upper limit a little bit because I want to chop it into 2 segments. The first segment is that I'm going to integrate this up to B, right? Integrate up to B covers that. And then I want to integrate this from B to plus infinity. Not only that, my lower limit has also to be changed from A to B, but I also need to include another case, which is from minus infinity to A of a 0, a dt. Very very complicated, right? But ultimately, the answer will be 1. Okay, I'm just going a little bit backward, reverse engineer, tell you where does this 1 come from. This 1 comes from the cumulative sum. Cumulative sum means that I want to integrate from minus infinity all the way to a point x here. Then, of course, I need to integrate this segment first, the second segment, and then the third segment up to my point x. So that corresponds to the first one, which is 0. The second one, that will give you 1. And the last one will give you 0. Okay. And this is not, this is not infinity. This should be x. Okay? This should be x, because you integrate up to the point x. So that, when you take this integral, it will give you 1. Now, once you're familiar with this integration, then you can skip all the steps. You can just say, hey, I've already integrated over the entire sample space. It's got to be 1. Right? So you can make that argument too. Okay, so that example tells you how do we calculate the CDF over the entire real line, not just the middle stuff. I hope that is clear to everyone. Is it okay? Let's work on another example in case you are still figuring out how to do it. So this is an exponential random variable. We have calculated the expectation last time. So this time, let's talk about the CDF. So the shape of this exponential PDF is like this. It is decaying from lambda to 0 with a certain rate. Then as I am integrating this PDF from 0 all the way to a point x, I am looking at the area under the curve, and I'm going to map it to the height on the CDF. So I'm going to do that. And how many segments are there in this PDF? From minus infinity to plus infinity. 2 segments, okay? 1 on the negative side, 1 on the positive side. Okay, great. So let's look at the negative side. Negative side is that I want to integrate, okay, anything from minus infinity all the way to x, and then there is a dt. What should be the PDF? What should be the PDF here? There is no PDF. It is 0. Because my PDF is defined only for the non-negative x. And so now I'm looking at the case where x is less than 0, so your PDF is 0. So life is good, you get a 0. Okay. Now, how about the positive case? When x is bigger than or equals to 0? Then you need to integrate. Okay, integrate your lambda e minus lambda x t dt. Where should be the range? Someone says minus infinity to x? 0 to x. Okay? Okay, so the answer is from 0 to x. The reason is that whenever you put down this formula, it means that you have stuff. But anything that's less than 0, you don't have any stuff. So you have to start with 0. If you put minus infinity and you try to integrate this one, you get plus infinity. This integral is it will just diverge, right? So you want to start with a 0. Now, how do we calculate this integration? This integration is not too terrible. Okay, so it is lambda integration from 0 to x e minus lambda t dt. So how do we do that? Substitution, right? Okay, let's do it. I need help. So it is going to be lambda here, minus 1 over lambda, e minus lambda t. Am I right? Okay. You hold the responsibility, okay? Okay. So this is going to be 1 minus e minus lambda x. Yes, okay, this is right. So the tips is that please read your calculus textbook. Okay. Okay, good. So that is that's the CDF. Now, does this CDF make sense? This is something that I always emphasize to all my students. Whenever you get an answer, ask yourself whether your answer makes sense. Is this function a monotonically increasing function? Is it? Let's check. As x becomes bigger and bigger, your e to the power minus lambda t will become smaller and smaller, and therefore this sum will be getting closer and closer to 1. So it is increasing. It is increasing. Will it go above 1? No, because the biggest one you can ever have on this e will be 1. So or 0. So you will be bounded between 0 and 1. It is a continuously moving up function, so it should make sense, right? So that's another example for the. This case is the exponential random variable. We find the CDF. The CDF contains two ranges, x less than 0 and x bigger than or equals to 0. So we find it. Okay, so now let's talk about some properties of the CDF. As I keep mentioning, that these three properties should always be there. The CDF is non-decreasing. It is not necessarily monotonically increasing. You can have a flat CDF. Just think about a discrete case. You have staircase function. Those are non-decreasing, but they're not monotonically increasing. You have a maximum occurring when your x is plus infinity, which is 1. You have a minimum when you are evaluated at minus infinity, which is 0. So this thing tells you that if you do whatever problem, you tell me this is your CDF, I don't even need to grade it. I would say this is wrong. Why? You get a negative thing. This is the first thing I can tell. Another reason why this cannot be a CDF, you have oscillation. It cannot be. It got to be going up. Things like this, that can be a CDF. Okay, it starts with 0. It goes up gradually. You can have a 0 slope. That's allowed. We just don't go down. Property number 4 is about the continuous random variable. When x is between a and b, you want to evaluate the probability. This is going to be f evaluated at b minus f evaluated at a. Now, there's something interesting here. Why is this true? Right? Probability x is between a and b. Why is it just the difference between the CDF at b minus the CDF at a? Well, we can write down the integration. This is the integration from, just look at this formula, right? You're looking at the probability from a and b, so you need to integrate from a to b on your fx dx. And this is the same as you say this is going from minus infinity to b, fx dx, minus integration from minus infinity to a of fx dx. Okay, so this integral, this finite integral from a to b can be written as the difference between these two finite integrals. And then the first one would just be f at b minus f at a. So that can tell you the probability between a and b, which is the difference between the two CDFs. So pictorially, how do we understand this? Let's say here is your PDF, and this is your CDF, right? And then I ask, hey, let's calculate the area under the curve. This is my A and B. Then I say, look, I go to the CDF, find out the B, find out the A. So here is your B, here is your A, okay? And so this point is F at B, this point is F at A, and so then you find the gap. The gap would be F at B minus F at A. This is corresponding to the area under the curve that you have integrated. Question? Can the CDF start from a negative x? Yes, the CDF can start with a negative x. I can give you example where this is your 0, your PDF is here. Okay, then your CDF will start at the negative value. That is allowed. So here is an example, exponential random variable. This is the PDF, this is CDF is given to you. I want to find the probability between 1 and 3. So you can take two approaches. You can say using the PDF approach, which is just the integration of your lambda e minus lambda x dx, going from 1 to 3. Then you solve the calculus, you get to this result. For the CDF, you say this is going to be fx at 3 minus fx at 1. And since the CDF is already given to you, you can plug in. You can say this is 1 minus e minus lambda times 3 minus 1 minus e minus lambda times 1. So you solve this algebra problem, you get this same result. Yes, question? Would that be negative? Yeah, of course. And so you need to change this to that. Okay. So thank you for finding this out. Okay, so you got to be this minus the other one. Here is another example. So you have this PDF, which is 2x. I want to find a CDF. So what is a CDF? The CDF will be, you should have 3 range, right? You should have 3. So let's look at the middle one. The middle one will be the integration from 0 to x of my 2x. My 2x, I need to change the variable to t, so it will be 2t. Then if I do the integration, that will give me a t square from 0 to x, so that will give me an x squared. Now, I also have x less than 0 and x bigger than 1. So for x less than 0, my fx will be 0. For x bigger than 1, my fx will be 1, just to cover the entire range of real line. So this is my CDF. Then I ask, oh, okay, what is the probability that x is between 1/3 and 1/2? So then I know this is a CDF, so it will be CDF at 1/2 minus the CDF at 1/3. So you get 1/2 because I've already defined it, so it will be 1/2 square minus 1/3 square, which will give you 5/36. So the exact calculation, to me, it is not as critical. The critical thing is that to understand the properties of the CDF, the shape, and then some discontinuity of the CDF. That is more important. So talking about the discontinuity, let me introduce this concept. Another concept in calculus is called the left continuous, right continuous, and continuous. Now, this function, a function, okay, an arbitrary function f is said to be left continuous at a point B if this equality holds. So on the left-hand side, you have this point f at B. On the right-hand side, you have this limit where you're looking at b minus h, and then you set the limit of h going to 0. So if this equality holds, then you say that f is left continuous. If you change the minus to plus, you get a right continuous. If a function is both left continuous and right continuous, you say that it is continuous. Okay? So lost? Yeah, good. So let me show you a picture. Let me draw it. Okay. No one can understand what they mean, right? So here is the thing. A function, when you talk about f right continuous, got to be something like this. Right? If it is smooth, there's nothing to talk about. Okay, so here is a point, B, on the x-axis. Okay, on the x-axis, there's a point B. There are two values. Okay, the first value, the other value. Now, clearly, this function is not defined at this point. It's not defined at this point. And I want to find out the empty circles, the two different values. Okay, let's talk about this empty circle. What is this value? This is f of b. Okay, f of b, but this is not defined. Where is the defined range? It will be b minus h, right? A little bit on the left-hand side of the b. That is well defined. So b minus h, right? So let me say this is, there's a h here, so this is b minus h. B minus h will be somewhere here. This is a well-defined value. So b minus h, b minus h. Now I want to calculate the value of this point. Of course, I just put the limit of h going to 0. Okay, so this value is limit of f of b minus h. Then you can imagine that what is the value of this point? It will be f of b, what kind of h? Plus h, okay? Plus h, and then set a limit of h going to 0. That is the value at this point. Now, if I tell you that this limit equals to that limit, how can it happen? There's only one scenario that can make it happen. Is that the two circles, they are the same. So you have a continuous curve. You look at this point here, then of course this limit will equal to that limit. Then you say it is a continuous curve. Now let's say that these two empty circles, I still need to fill up the value. Now I have two choices. Let's say I fill up the values over here. Okay, whereas the other case is that I fill the value down there. So when I fill up a dot, I mean that FB is over there. This is FB. So when FB is up there, then FB will equal to this limit. This limit. So the case here is that my f of b will equal to the limit of f of b plus h. This is h going to 0. The other case, here it is that fb equals to the limit where f of b minus h, h going to 0. So this thing is called right continuous. This is called left continuous. Depends on where you put the solid dot. If you put the solid dot on the top, this is called right continuous. Not necessarily on the top, but you can at the bottom, okay? But it has to be the solid dot on the left-hand side. This is called the right continuous. I know it's confusing, left and right, okay? But it's called the right continuous. This is called the left continuous. Okay, if a function is both left and right continuous, you say that it is a continuous function. So that is the meaning of all these crazy words. A CDF is left or right? Make a guess. Is it left continuous or is it right continuous? Is it left continuous, right continuous or left continuous? Which one? Which one? Should you define the solid dot here or should you define the solid dot there? see. For any random variable x, this CDF is always right continuous. The solid dot is always on the top guy. Remember that. Okay? And why is this the case? It's because when you evaluate the CDF, you say that fx equals to the probability that x is less than or equals to x. Equals to is included. Your equals to is included, and therefore it got to be the upper one. Okay, so this is the right continuous property of the CDF. Now, the right continuous property of the CDF will immediately bring you to this jump property. This is also a pretty important property. Whenever you see a discontinuity, there's a jump. The jump has a height in the CDF. The height will tell you the probability at that point. Okay, whenever you see a jump, the jump will tell you the probability at that point. And this probability is evaluated as the difference between the solid dot and the empty dot. The empty dot is found by the limit. You start with this curve, and then you set the limit going to 0. Then you can find this empty dot. You calculate this difference. You can find the height of the jump. Okay, so this is very confusing. Let me work on an example to make sure that it is clear. So consider this PDF. This PDF is arbitrarily made. Okay, it has what? It has 3 segments. In fact, it has more. It has more segments. The first one, it is x between 0 and 1. You get x. When x equals to 3, you get a pulse of 1/2, and then it is 0 otherwise. So that is the PDF. And let me show you the shape of this PDF. The shape of this PDF is like this. You have a triangle followed by a bunch of zeros, and then you have a pulse. Okay. Don't ask me how can you construct this PDF in real life. No, okay, it's just something I make up to illustrate the property. So this is your PDF. This is the CDF. Without doing all the calculation, just drawing you the CDF. The CDF should look like this. And let's see if it makes sense without doing the calculus. See if it makes sense. So whenever you are less than 0, it should be 0. That's okay. And then as you are integrating this thing, because you're integrating a triangle, you should get a quadratic equation. So it should go up. Where should it stop? It should stop at 0.5 because that triangle occupies half of the probability. So you should go to 0.5. And see, once you're at 0.5, you should stay there for a while until you hit the number 3 because you do not have any mass to accumulate. Once you hit the number 3, you see a jump. When you see a pulse, therefore you should have a jump. The jump will give you a height of 0.5, which corresponds to the height of this pulse. And once you are there, you have this right continuous property. You put a solid dot on the top guy, and then you will stay there forever because this is 1. All right? So without doing any calculation, I convince you that it makes sense to have the CDF with this PDF. So now let's work on some calculations. For the range of x between 0 and 1, that is just the integration of whatever from 0 to x, and then there's a x, so I have a t dt. So I have x squared divided by 2. So that is a CDF for this range. For x is between 1 and 3, between 1 and 3, what should be the value? 1/2. Okay? 1/2 comes from the fact that you have already accumulated 1/2 of the probability. And so this is just the integration from 0 to 1 of your t dt. So that is going to give you 1/2. Okay? You integrate this entire triangle. Here, you integrate this triangle up to a point x, where x is still inside the triangle. And here, where you integrate the entire triangle. So that will give you 1/2. That explains, okay, so I have explained this segment. I have explained that segment. And clearly, anything before a 0, it will be 0. So now let's look at the point 3. Let's look at the point 3. At point 3, the diagram says that you have a pulse. You have a pulse. So the CDF at this point will just be let me see. Okay, it will be whatever you have left. Okay, whatever you have left. So, okay, it would be the probability where x is less than or equals to 3. Okay, so it will be probability of x less than or equals to 3. So you look at this PDF, you need to integrate. You need to integrate from 0 to 1 all the way to 3, including the 3. Now, if you were before 3, you get 1/2. And then if you include the 3, it will be 1/2 plus the other 1/2. This is coming from the triangle. This comes from the pulse. So 1/2 plus the other half, so that you can calculate this probability. That will give you 1. Now, when x is bigger than 3, you don't have to do anything. You just integrate from -infinity to infinity of any fx dx. That will just give you 1. That's very easy. Okay, so then you can write down, this is the CDF. The CDF, you have 4 ranges, 0, less than 0, between 0 and 1, 1 and 3, and bigger than or equals to 3. So you have 4 segments, and then each one you have a value, which corresponds to this plot. So now let's talk about the reverse direction. Okay, the reverse direction. I give you the CDF, find me the PDF. How do we do that? So here is a very useful theorem, which we have already seen before. It's called the fundamental theorem of calculus. It says that if you have a CDF here, you take the derivative with respect to x, you're going to get something inside. Okay, so that is the PDF. Now, look, there are 2 cases here. The first case is that if the derivative is defined, okay, if fx is differentiable x, then you take the derivative. If fx is not differentiable x, then think about that. You have a jump. Okay, you have a jump. So whenever you have a jump, then you will give a pulse, right? So that's the reverse direction. I give you this curve. Anything in between, you can just take the derivative, right? Derivative here will give you the slope, which is this x. Derivative here will be 0. But when you have this discontinuity, you have a jump. Then you wouldn't have this derivative. You would convert this height to a delta function with a magnitude of the height. So let's do an example. So here is a CDF with this expression where you have this pulse followed by a exponentially decaying function, and this is your CDF. I want to start with the CDF and go back and find the PDF. Right? So I start with the CDF. So how do I do that? Well, I can divide the CDF into 3 segments. When x is less than 0, then my fx will be, well, less than 0, right? It will be 0. We don't have to do anything. When x is bigger than 0, I have a continuous function. Then you just take d dx of your fx, which is your fx. So you have d dx of your 1 minus 1/4 of 1 minus 2x. And you do the calculus, you get 1/2 of e to the power minus 2x. How about when x is 0? When x is exactly at 0? when x exactly at 0, you see there's a gap. There's a gap. The height of this gap is 3/4. Okay? So this is going to be 3/4 times a delta function. Or if you just write 3/4, it's also okay to me. If you want to be precise, it would be 3/4 times a delta function. Let me see. Okay, so great. So this is a summary slide summarizing the CDF. So the definition is given by this. So your CDF is the cumulative sum, and then your properties, non-decreasing, 0 and 1. If you're looking at the interval, is the difference between the two CDFs. Right continuous, so it's a solid dot on the start. Okay, so that's a pretty good slogan to remember. And if it is discontinuous, then the probability at B will be your gap. Okay, so as we come back after the October break, we will start to talk about a few very concrete examples of these continuous random variables, and then we'll talk about especially the normal random variable, and to tell you more about why it is so useful. All right, so have a wonderful October break.